S8.5 and S8.6 are about two topics called permutations and combinations, and they're very closely related, so I suggest you do the homework for these two sections in close proximity. Do them like on the same day or at most one day apart. They're both based on a key idea called the fundamental counting principle. And the fundamental counting principle is meant to be pretty intuitive. Like in this particular problem here that we've got on the screen, we're talking about research design. How do you set up a study in order to investigate, in this case, investigate exercise and meditation and how they affect blood pressure? So if you've got 4 different exercise programs and you've got 3 different meditation types, and you're trying to figure out all the various combinations of exercise with meditation, if you think about it, you could draw a picture, and that's okay if you're doing a problem that only has like 4 different exercise possibilities and only has 3 different meditation. I said 3, so I wrote 3. 3 different meditation possibilities. But if you had 20 different exercise possibilities and 37 different meditation possibilities, there's no way you would actually draw the chart. But still, the key idea is, and this is the fundamental counting principle we're talking about, the key idea is you multiply the numbers together in order to figure out the number of possibilities. So the fundamental counting principle is basically just saying you multiply together independent pieces of something in order to figure out the total count of how many different ways to do something. And of course, in this problem, we've also got the additional little twist that in order for statistics to work, you have to have 30 subjects in each category. So we would also throw a times 30 on here. But that's not the fundamental counting principle. The fundamental counting principle is this part here in red. The fundamental counting principle gets a little trickier to understand when the things that you're multiplying together aren't completely separate like they are in this case. In this case, exercise possibilities and meditation possibilities are clearly totally independent. They've got different names if nothing else. But take a look at this example here. In this example here, we have a club. The club has 8 members, and they're trying to pick a president and a vice president and a treasurer. And they don't really care who does which jobs. They just have to fill out the paperwork so that the school will approve their club. So they're just going to pick these people at random. They don't want to get into an election where people are going to get their feelings hurt. So they're picking these people at random. And the question we're trying to answer is, how many different boards might they end up with? So here's what you should be imagining. Imagining they've got this hat. They've got the names in the hat, and they reach into the hat and they pull out a name for president. And then they pull out a second name for vice president, and then they pull out a third name for treasurer. Well, think about how this is going to work. When they first reach in and pull out a name for vice president, there are 8 names for president, there are 8 names in there. So there are 8 possible ways they could pick the president. But when they go into the hat to pull out a name for vice president, whatever that first name was, it's not in the hat anymore. So there's only 7 possibilities left. And then when you get to treasurer, 2 names are already out of the hat. Now there's only 6 possibilities left. So here, although each choice is independent, sort of, they're also coming from the same list of names, so they're also kind of linked. And that makes it a little trickier to think through, but ultimately, you do end up using the fundamental counting principle. You do end up multiplying together all the possibilities. 8 possibilities for president, 7 possibilities for vice president, 6 possibilities for treasurer, and that ends up giving you 336 different possible executive boards for this club. Now, looking at what we've got going on here, this leads us to a very important topic that we're going to be using in both this section in S8.5, and we're also going to be using it in S8.6, and that's the idea of a thing called factorials. Factorials are related to this example we just did, except they work by just sort of continuing this pattern as far as you can. And the symbol for factorials is an exclamation point. So you look at this and you think it's saying 8, but it's not an exclamation point like in the English language. It's a mathematical symbol. And what it stands for is start with this number and multiply by all the previous numbers as far as you can. So 8 times 7 times 6, that's not as far as you can. You could go to 5. You could keep going 4 and 3 and 2 and 1, and that's pretty much where you'd have to stop, because if you went any further, your next number would be 0. And if you did that, then every factorial would come out to be 0, and it would be kind of boring. So here you would get, not 43, 4,320 altogether. 40,320. One little tricky part about factorials is what happens if you look at smaller factorials. Bigger ones get bigger very fast. You end up with very large numbers very soon. And in fact, that's why they picked an exclamation point to use as the symbol for factorials. But the interesting stuff happens if you make your factorials smaller. Like, for example, 7 factorial is 5,040. 6 factorial, 6 times 5 times 4 times 3 times 2 times 1, that's 720. And I'm writing them this way in sort of a hopefully fairly suggestive fashion where I'm trying to hint at something. 5 factorial is 5 times 4 times 3 times 2 times 1. It's important to notice that each smaller factorial was kind of already in there in the previous ones. And in fact, all that's happening as you go down this list is you're losing one of the factors. So to go from 8 factorial down to 7 factorial, you lost the 8. The 8 dropped out, so it's effectively divide by 8. And to go from 7 factorial down to 6 factorial, the 7 dropped out. And from 7 factorial down to, from 6 factorial to 5 factorial, the 6 dropped out. And you can keep doing this. 4 factorial would be the 120 we had a second ago, and then just sort of lose the 5. You get 24. And you could keep doing this. 3 factorial, you would divide the 4 out from the 4 factorial, and you would get 6. 2 factorial, you would divide out the 3 from before, and you would get 2. 1 factorial, you would divide out the 2 from the previous one, and you would get 1. And here's the part that catches people by surprise. This pattern can go one more step. There's no reason why it would have to stop here. We were doing divide by 8, then divide by 7, then divide by 6, then divide by 4, then divide by 3, then divide by 2, then couldn't you do divide by 1? Well, yeah, of course you can. So you would get 0 factorial equals 1. But then the pattern has to stop. It can't go any further. Divide by 0 is undefined. That's not going to change just because we're doing factorials. So there is a 0 factorial. It equals 1 because that's what fits the pattern, but that's the end of the factorials. It doesn't end at 1 factorial. It ends at 0 factorial. And that's actually going to matter. We're going to see 0 factorial showing up in problems in the future. Now, all of this here is really just the beginnings. It's what we call the fundamental counting principle. The topic we're supposed to be talking about is permutations. And permutations link to section 8.6, which is about combinations, and it's really kind of important to talk about them both at the same time. So permutations and combinations both relate to situations kind of like what we had with that club problem, where there's a group, and in that case it was a group of people, but it could be a group of playing cards, it could be a group of numbered ping pong balls in a bucket like you're playing the lottery. The group of things that you're picking from could be really just about anything. So when we talk about picking from a group of n things, those things can be anything. People, cards, anything. Then you pick some of them, Like in the club example, we had the 8 people and we picked 3 to represent the club. If you're playing poker, you've got 52 cards and you pick 5 of them. So there's 2 numbers involved here. How big is the group, and how many are you picking from the group? Another vital thing is that you can't put things back. Like when you're picking people to represent your club, you can't pick a name for president, put the name back in the hat, and then pick that same person to be vice president. You can't replace them. Same thing in playing cards. If you're playing poker and somehow you've got 2 8 of diamonds in your hand, you must be cheating. There's no way you can have 2 of the same thing. The main difference between permutations and combinations is right here. If you are doing permutations, the order matters. Like if you're picking people to be the president, vice president, and treasurer of a club, a different order to the same names is actually a different executive board. Even if person A is the president and person B is the vice president, if you switch that around and have B be the president and A be the vice president, that's different. Now compare that to a poker hand. If you've got 5 cards in your poker hand, it doesn't actually matter which one was first and second and third. You've just got those 5 cards. So that would count as a combination. Combinations are what we're going to be talking about next time. So come back for section S8.6, and that's where we're going to talk about combinations. Now, permutations. Permutations are kind of straightforward because we sort of hinted at them already from when we did that problem with the club members. So if you have a group of n things, like 8 or 52 or however many things, and you're just picking one of them, then there are n different ways you could pick them. Like the president for the club, we had 8 choices because there were 8 names in the hat. If you pick 2, then you take that and you multiply by 1 smaller. Like with the club, we did 8 times 7. There are only 7 names for the second choice. And that continues. If you're picking 3 things, then you're going to have n times n minus 1 times n minus 2, and so on. As an example, if you're doing 17, pick 4, and I don't know why, maybe you have a club with 17 people and you're picking 4 positions, something like that, then you're going to start with 17 times 1 smaller, 16, times smaller than that, 15, times smaller than that, 14. So notice, looks like the beginning of a factorial, doesn't it? It just stops after the first 4 numbers in the factorial. Then you multiply that all out, and you get 57,120. There is a formula for this, sort of, but it's not really a super practical formula. The formula is that you go n minus 1, n minus 2, n minus 3, etc., and you take r terms. And that might sound okay when we did our first example of 17p4, where we picked 4 starting from 17 and counting down, because 4 numbers is not a lot of numbers. But if you're trying to do, like, say, P5213, that's an example of, like, if you're playing bridge. There, that's an example. You have 52 cards, and you get 13 of them in your bridge hand. Then this formula is really pretty awkward, because you're supposed to go 52 times 51 times 50 times 49 times 48 times 47. Wait a sec, how many of these am I going to do? I'm going to do 13. 1, 2, 3, 4, 5, 6. I've only got 6 so far. 46, 45, 44, 43. Man, this is tedious. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, keep going. 42, 41, 40. Am I there yet? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ah, there we go. So you see, this this formula is actually pretty terrible. It works fine when r is small, but when r starts to get kind of big, this formula is not really very good. In order to make this formula better, first let's pause and talk about a special case when you've got a situation where you take everything in the list. So if you had 8 people and you were picking all 8, or you have 52 cards and you pick all 52 of them. In that case, this thing that looks like the start of a factorial, it would keep going. It would keep going all the way down to 1. So you would actually end up with a for real actual factorial. So if you have the two numbers in a permutation are the same number, the second one isn't smaller, it's the same as the original one, then you actually get a full-on factorial all the way down to the bottom. So, okay, let's see if we can do a better than this. So you look at something like this, and of course you think, is there something better? And the answer is yes. So the something better feels kind of weird at first. What we do with something like P5213 sounds like the exact wrong idea. We actually continue going past 40. So, for example, you would normally stop at the last number in the list, but here what we do is we keep going all the way down to 1. With all these extra terms, though, those extra terms aren't really part of the answer, so you also divide them out. Okay, that seems like a terrible waste of time. Why would we put them all in there just to later on remove them? That seems completely silly. Well, the reason why it's a good idea is because that numerator now is a full factorial all the way down to the bottom, and so is the bottom. That starts with whatever number n minus r is, and then drops and drops and drops, just like a normal factorial. So here you end up getting a formula that actually can be typed into a calculator because, surprise, your calculator has a factorial button. Depending on what kind of calculator you've got, it might be over on the left in blue where you have to press second, or maybe it's under some sort of probability menu because they usually hide them in the probability menu. But I'm pretty confident if you have a scientific calculator, there is a factorial button somewhere. And that means instead of having to do a problem like we did in green up here, 52 times 51 times 50 times 49 times 40, even with a calculator, that's just tiresome to type all those multiplications. Here, we can turn P5213 into a calculator problem that's much easier to type. You would just have to do, on the calculator, 52 factorial divided by 39 factorial. So, notice, 52 minus 13 equals 39. That's how you figure out the denominator. Okay, so let's do that. Let's grab the calculator, type that in. Oh my gosh, you get a huge number. Your calculator will give you this answer in scientific notation, because this is a gigantic number. It'll say 3.9542426444. I don't know how many digits your calculator is going to have, but it's going to say something like that, and then it's going to say times 10 to the 21st power. It probably won't actually say times 10 to the 21st power. It might say something like 3.954242644 E21. That's a pretty common thing to see on a calculator. They often display their answers like this. So that E on a calculator, that stands for scientific notation. That means times 10 to the 21. And this is a really huge number, and I want to make sure you understand just how gigantic this number is. So remember that P5213, this is the number of different hands you might get in bridge. So this is the number of different bridge hands that are possible. And people play bridge. I mean, I played bridge once or twice. I didn't really enjoy it. It's kind of complicated, but if you're really into it, it turns out to be a pretty interesting strategic game, apparently. I know some people who play bridge and they really like it. So if you're counting the number of bridge hands that are possible, let's imagine that you were going through all the possibilities one at a time, and let's say you were doing it very quickly. You were doing each bridge hand once per second. How long would it take to go through all of them? Well, 3.9542 times 10 to the 21st seconds. Well, wait a sec. I don't know how long that is. It's just a big number in my head. It doesn't sound like a lot. So let's divide by 60 to get minutes. Okay? So you take that number on your calculator, you press divide by 60, and it's still scientific notation. It's 590404406 times 10 to the 19th minutes now. Okay, well, it still doesn't really tell me how long it is. I don't have a feeling for it. So let's divide by 60 again, and let's get hours. Well, it's still a really big number. Okay, so I still don't really feel like I know what I'm talking about. So then, let's take the hours, and let's divide by 24 to get days. So it's taking days, it looks like. It's still scientific notation. I still don't really know what I'm talking about here. So, okay, let's divide by 365 and get years. It's going to take years to go through all the different bridge hands. It's still scientific notation. So if you've got 1.253882117 times 10 to the 14th years, realize that that means you move the decimal point 14 places. So you're going to get, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 years. That's thousands, millions, billions, trillions. That's 125 trillion years to go through every single bridge hand, even if you're doing one every single second. And what that kind of means, and I remember one of my friends who plays bridge, one time they said that each bridge hand is a miracle because they're so unlikely. Any one bridge hand, you would never see that bridge hand again. If anybody ever says that they've seen the same bridge hand before when they've done a problem, that's complete hokum. There's no way that any two people have ever gotten the same bridge hand. That's 125 trillion years to go through every one of them. That's nuts.